Hello, today I'm going to be presenting my project, design protein for blocking snake venom. The problem is that more than 100,000 people are dead, are killed by snake bite poisoning, and there is like a 400,000 who live survivors, but with um, amputation, kidney harms. So not mostly it happened in South Asia, Latin America, and Sub-Saharan Africa. How the snake venom paralyzed, and this is something that happened in just a family of snakes called elapids that they kill by paralyzing the animals. So normally it what happened is in normally the nerve communicates to the muscles through ACH, and the muscles has a receptor here for ACH that made the muscles contraction, and the toxins from this lipid, what they do is blocking the receptor of ICH, and the muscle don't move. Muscles the time the animals who receive the bite die because of respiratory crisis. Is the yeah. How is this solved? And normally we don't want to break the toxin apart. We just want to design a binder that attach to the receptor in the toxin, like this here. This is the binder, and it attached this protein attached in the receptor binding patch, and it doesn't let this protein to attach to another protein. So it is in some way block the toxin. What I have done before is Basket and Torres. They designed a protein that neutralized the cobra toxin, which is the venom of the cobra, and who kills. They did that in a pretty big cluster sampling, more than 10,000 tries for design. The computational pipeline for building this protein is basically the first step is RF diffusion, which create the shape called backbone for the protein. It's just the shape, doesn't contain any amino acid. And the guide for using for creating that is hotspot. You can tell the RF diffusion program where it's going to be the hotspot that attached to the other protein, and also you can do like giving the model similar structure, and the model is going to try to follow that structure. That's called conditional folding, if I remember well. And the second stage, once you have the structure, given that structure, you want to know what is the amino acid most likely to have in this structure. And that's the word for protein MP and N. And once you have these two steps, you have the full protein, but you want to evaluate that. You want to know how good are them. So this is the phase three when you pass the protein or to AlphaFold, and AlphaFold is gonna tell you how good is this the protein, is the shape of the protein, as the amino acid makes sense, and it gives you like metrics. So some of the metrics are here, and this is part of the computational filters for taking a protein to the lab whenever it passes all the filters. Normally is having like this I pi less than 10, the PLDT higher than 0.8. So this is part of the problem. And I really like this aspect, the deciding using AI for creating proteins. And I tried to tackle a similar problem. I realized that the Krait, the Taiwanese Krait, uh, this snake here is kind of similar to the cobra, They are in the same family. They are elapids. They have the same toxin family, and they have kind of the same receptor target. So, and they share like 65% of the toxin. So I review the literature and see that nobody else attacked this problem as I know. And then that's the objective of my work. Try to predict a protein for neutralizing the toxin in the krait. So as I mentioned, what's still missing? Vasquez and Torres solved this, and we'll be trying to solve this. Yeah, this is like a summary. This is the two protein. I run different tests, different strategies, and all these like this Google Colab Pro GPU. It's not that much, but we'll see what we got. Yeah. The first the first idea I have is transfer the hotspot from the cover toxin and try to transfer that knowledge to build the protein for the bungaron toxin. So I did that with the hope that this is going to work or it's going to be kind of be similar, but it didn't work. So it was a total failure. And then my second idea was, well, I want to see how this is. I can see the where the bungarotoxin attached and how it attached to another cell. And I investigate that it attached. There is a crystals where this protein is attached to another cell. I went there, measured the hotspot where the protein attached, and let's design this 2 by 2 uh, criteria or experiments. One was with the MAPEC hotspot from the cobra and this is the size of the protein. When I tried this C1, it failed, as I mentioned. Then I increased the size of the protein for make it more more likely to attach to the toxin, but it didn't work. Then I see the real bungarotoxin, where it attached and how it attached to another cell. And I create a protein for attaching that hotspot, and it didn't work. And when I combine the size, increasing the size, and also uh, using the same hotspot I saw in the crystal, there was one of the protein that passed all the filters. I got 6.8 in the IPI and 0.78 in the IPTM, which is like 85%, 87% what the cobra toxin did. And we get that. The IPA for the cobra toxin is 5.9, so we are pretty similar here. So I call this protein the BGT88 version 1. This is the real rendering of this. I can show you here how it looks like. It looks like that. Let's check here. This is the how it looks in 3D. The gray one and the red one is the toxin. The blue one is the protein I designed. And yeah, you can see here the red area here is like the receptors or phase receptors that attach to the muscles. What the protein, the blue protein do is it attached there. So the toxin, once they are attached, the toxin cannot work, not fit into the muscle. It's neutralized. That's the main contribution of this research. So I can show you here passes the part of the metrics, and the metrics are, as I mentioned, 6.8, 0.91, and the only one I got like doesn't pass a filter in theory. Was the RMST, which is should be less than 2, and it was like 5.94. But however, it doesn't validate the. It's like a secondary metric. It's not the most important. The most important one is the first two. And the reason why it doesn't invalidate the result is because AlphaFold has five models for evaluating the protein. And all the five models uh, predict that the protein is going to attach exactly in the point what we need for blocking the toxin. So that's something that we can dig on. We can use this first candidate for having like a more experiment and try to cross the threshold. So hopefully we'll hopefully get that. Where we are in the pipeline, we did the computer design, we did the structural check. We can dig even more for having better proteins. We have to check in the lab how it works, if this neutralize reality the toxin, and the final stage is to testing in animals. That's it. Basically, the my job design this novel because this new protein doesn't exist in the nature. It's not like a natural. It's an artificial structure. So that's it. I hope you enjoyed this, and I want to thanks to Dr. Jim because the idea of this project was for AI in healthcare, and the idea or the objective is try something that is difficult, and you can whatever you is the result. If you try hard, you'll pass the course. You have to grade. So thank you so much for your time. Hope you enjoyed, and thank you so much for Dr. Jane.